Hello AP Physics 1 students. Make sure you have your problem set in front of you. We're going to start here with problem number 5. Go ahead and read it on your own, pause the video, try it, and come back to see how I go through it. Okay, so we're looking at a wire with a current here, and we know that, of course, we developed an equation last class for the magnetic field produced by the wire with the current. And that equation is given by V equals mu naught I over 2 pi r. I is the current creating the magnetic field. These two are associated with each other. Mu naught is that constant, the permeability of free space, and r is the distance from the axis of the wire over the location of space we're looking at. So really it's just a matter of putting the right numbers in the right places. It's always going to happen that we have 4 pi on top and 2 pi on the bottom, so you can really just automatically cancel those two out, leaving a 2 times 10 negative 7 centimeter per ampere on top. And of course this is in centimeters. Make sure we convert it to meters. You put your numbers in, you get 8.57 times 10 negative 6 Tesla, or 8.57 micro Tesla. That's very typical. Magnetic fields of a whole Tesla are very, very strong. It's only in a laboratory you'd see something like that. And so from this, even 3 amps is not a small amount of current. That's a pretty large amount of current, and still a pretty small amount of field. That's a very typical sort of number. But it does ask for magnitude and direction. And so for direction, we know it's going to be a right-hand rule. We now have a couple different right-hand rules. We want to make sure we know which one it is. So is this going to be the one with pointing or the one with grabbing? So pointing ones are always for forces, but we're not dealing with force, we're dealing with field. Remember, anytime we're dealing with either force or field, just take that extra second to make sure you really know what you're finding. And capital B here stands for magnetic field, and this is going to be the grabbing one. So here's where you're going to grab the wire with your right hand. I like to grab something tangible, so hold your pencil or pen in your left hand, and then with your right hand grab the wires. Remember, your thumb is going to be pointing with the moving charges, the conventional current. That's towards the bottom of the page on your paper, or if you're doing with the screen, it's the bottom of the screen. You wrap your fingers around, and we draw these sort of continuous loops going around. Make sure it's a broken loop so you can see where it's passing in front and passing behind. And the direction your fingers are pointing, that's the direction of the magnetic field. So in the front of the wire, it's pointing to the left. Behind the wire, it's pointing to the right. And then you might want to extend some more of those magnetic field lines until it gets to where point P is, so you can really tell which way the magnetic field is pointing at that location. We also want to practice doing with dots and X's. Remember, my advice for this is take your imaginary wire, which is your pen or pencil, put it right up against your paper. Put it on your paper, and then with your right hand and your thumb pointing to the direction of moving charges, try to grab that wire. You should feel, in a very tangible way, your fingers hitting the paper on the left-hand side of the wire. So if they're hitting the paper, that's a field that's into the paper. And then pull your imaginary wire a little bit off the paper, wrap your fingers completely around, and on the right-hand side, you'll see your fingers are poking up through the paper. That's going to be coming out of the page. And so on the left-hand side, it's pointing into the paper with X's. The right-hand side is pointing out of the paper with dots. And I like to sort of cluster them closer together near the wire and spread farther apart, farther away from the wire to show this relationship as R gets large, B gets small. Either way you do it, as you can either visualize this field line going into the paper there or X going to the paper there, we know that the magnetic field is pointing into the screen or into the paper, or you can write the X there. Any way you express it, that's the direction of the magnetic field. Alright, let's go ahead to problem 6. Again, read it, try it on your own, and come back to the video. Okay, so we're looking at the magnetic force on this moving point charge. Now, why is it feeling a magnetic force? It only feels a magnetic force if there's a magnetic field. Where's the magnetic field coming from? It's coming from the wire with current. So let's start here with the equation for the magnetic field produced by the wire with current, mu naught I over 2 pi r. You can put your numbers in. Again, make sure we're using proper units here. That's 1 centimeters, that's 0.1 meters. And this 0.75 meters, that's not what's included here, right? To be very clear, we're not just putting any sort of numbers in here. The R is the distance from the center of the wire over the location of where we're looking, and that's this location here. The 0.75 meters, while it is a distance, is not what goes in there. So make sure you're putting the right numbers in the right places. Put the numbers in, we should be getting 2.4 times 10 negative 4th Tesla. Again, a relatively small amount of magnetic field. That's good. But that's not what we're looking for, right? We're looking for force. This is field. This is where you stopped. You're not being careful enough. Remember, I warned you. Whether you're doing force or field, make sure you know what you're finding. So we're finding force. And what are we finding the force on? So that's going to help us decide which force equation to use. Should we be using QVB sine theta or ILB sine theta? Because look, we've got a point charge and we have a wire with current. And this is what I was warning you about last class. Alright, so hopefully you recognize we're finding the force on the charge, and so we are using QVB sine theta. It's the equation that has the charge in it, since we're finding the force on that charge. This field is the external field from some other object. That's the wire. That's the field we just found. But what about theta? Right? We know the charge. We know the speed. We know the magnetic field strength. What about theta? Where's theta measured? Well, remember, anytime theta is part of the equation, it always refers back to the two previous vectors. So we got the velocity vector and the magnetic field vector. The velocity vector is clearly pointing to the left. What about the magnetic field vector? Well, how do we figure that out? The field is produced by the wire, so we have to figure out the direction of the field from the wire. Is that the pointing, or is that the grabbing? That's the grabbing. Remember, the grabbing is always for field. So, with your imaginary wire up against your paper, and your right hand with your thumb pointing to the left, you're going to try to grab that wire. Again, you should very tangibly feel your fingers hitting the paper above the wire. Pull the wire, or the pencil up off your paper, grab all the way around. Your fingers are sort of poking up out of the paper below the wire. And so we have field lines that point like this, or dots below, X's above. Either way you express it. I think the dots and X's are a little bit easier to see, plus you want to get used to that because that's the way the book is going to do it, and that's why you're going to see it printed on tests as well. You should see in the region above the wire where this point charge is, the magnetic field is into the paper. Okay, so the charge is moving to the left, the field is into the paper. What's that angle? That's 90 degrees, and we know sine 90 is 1, so that's going to go away. You put your numbers in, you should get 4.8 times 10 negative 4th newtons. But if you stopped here, you're doing all the sort of problems that I see on the test. You have to find direction, right? The problem asks for direction. You know on a test there'll be a point for direction. You have to find direction. So we want to find the direction of the force. How do we do that? Another right-hand rule. Okay, is it the pointing or the grabbing? This is the pointing one. We've already done the grabbing one. That's for the field produced by this. We want to find the force. And anytime we're doing force, it's always pointing. Okay, so with our right hand, we're going to point in the direction first that the charge is moving. That's the left. We curl our fingers in the direction of the magnetic field, and we've already shown that's into the page, right? So you rotate your wrist until you can comfortably curl your fingers into the page. Which way is your thumb pointing? Well, it should be pointing towards you or to the bottom of the page, or in the plane here, it's pointing this way. And so we can draw an arrow or write the word to the bottom of the page. Any way you want to express it is fine, but we should be getting to the bottom of the page. If I then were to ask you which way is the wire going to feel a force, well, even though we don't have to go through the calculations, we should be able to see by just figuring out that if this charge is pulled to the bottom of the page, this wire should be pulled to the top of the page by Newton's third law. Alright, let's go on to problem 7. Here we got 2 wires. Again, pause the video, solve the problem, come back. Okay, so in class, last time, of course, we developed the equation of force per length as mu naught I1, I2 over 2 pi r. We usually write it this way because it looks like the other force equation is constant times the product of the two objects involved divided by something with distance. And then just move the L to the other side to find the magnetic force. And, it's not typical math here. Put the numbers in. Just be really careful. Which is R, which is L? L is the length of the wire. R is the distance from one wire to the other, or really from one wire creating the field to the point in space where the other wire is sitting. That's why they're experiencing a force, because one wire is sitting in the field of the other. But be very careful that you know which is R, which is L. You cannot mix and match these, right? If that's confusing to you, go back and look at the definitions. And of course, this is given in centimeters. Make sure you put that in. Okay, so you got 2.73 times 10 negative 5th newtons. Great. But it does ask for directions. Now, be very, very careful. Are we finding the force on wire 1 or the force on wire 2? Read carefully. Right? We're finding the force on wire 2. Now, why is wire 2 feeling a force? It's because wire 1 is exerting a force. Why is wire 1 exerting a force? Because wire 1 creates a field. So whose field do we care about? We care about wire 1's field. We're finding the force on wire 2, but an object can never experience its own field. I've said that before, I'm going to say it again. An object can never experience its own field. So wire 2 feels a force because wire 1 is creating a field. So let's figure out the direction of the field produced by wire 1. Is this the pointing or the grabbing? Fields are always grabbing, so you grab wire 1. Now, this is kind of awkward. Since your right thumb has to point to the right and you got to grab it, I've told you before, if it's awkward, turn your paper. You can turn your paper any way you want to make this easy for yourself. Just make sure you turn it back before you start to write things. And you should be getting X's below the wire and dots above the wire. You should feel your fingers hitting the page over here, poking up out of the page here. All right, then you want to sort of extend those field lines over to the region where wire 2 is sitting, and I'm labeling it B1 because that's the field produced by wire 1. All right, so now we've got charges moving to the left and the field into the page. We're going to do a right-hand rule. Is this the point or the grab? This is the point. Okay, so our charges are moving to the left, field is into the page. We should be getting a magnetic force to the bottom of the page. And that's our answer here, to the bottom of the page. Now, as a little extension question, which way would wire 1 feel a force? Well, if you'd like to, there's plenty of space down below. If you want to go through the entire thing again, draw them again. Now you'd find the field produced by wire 2, extend it to the region of wire 1, and figure out that. But of course, we know what's going to happen. It's even shown right here by having the product of the two forces. We know the force magnitude is going to be the same, and Newton's third law says the forces are always equal and opposite. So we know that wire 1 we feel a force away, or towards the top of the page. These two wires are pushing each other away. That's kind of interesting. Let's notice that the charges are moving in opposite directions. So wires with currents pointing in opposite directions actually repel each other. Let's compare that to things we've seen before. Go back in your notes. If you don't have them in front of you, pause the video for a second, open up your notes when the first time we had done this, and let's look at that. Here's what that looked like. Here we had two wires, and the charges moving in the same direction, and we had the forces towards each other. So we see wires with currents pointing in the same direction actually attract each other. That's interesting. Here the statements are side by side. When they point in opposite directions, they repel, same direction they attract. We actually saw this already back in problem 6. Here are charges moving to the left. Here's an individual point charge moving to the left, and this point charge was attracted to this wire. And we already said that this wire would be attracted upwards towards this charge. So again, even though it's only a point charge, it is a current, right? It's a tiny current, but it's a current. And so charges moving in the same direction attract each other. Opposites repel, same attract. This is a little bit weird because it's actually the exact opposite of our usual sort of rules when we talk about point charges or poles of magnets. Opposites attract and likes repel, but this is different. This is exactly opposite. Opposites are actually repelling and same are attracting. Now, why is this important? Well, right now we're dealing with 3 amps and 5 amps, which are actually pretty large currents, but in a factory, lots of large machineries, the currents could be even larger than that. And of course, you're going to have charges going to the machinery and then charges leaving the machinery to complete the circuit, right? So here's a current heading towards a big machine. Here's the current leaving. Let's pretend they're the same current because it should be the same current, right? And so if we have these charges moving in opposite directions, they're going to repel each other. And with very large currents, these forces will not be inconsequential. It won't be 10 to the -5. It's going to be pretty large. And so if they're just left there, when they turn the currents on, these wires will push each other away so much they'll actually rip themselves away from each other and possibly disconnect from the machinery, causing some very dangerous situations. And so if you ever get a chance to tour a very large factory and you look for the wires, you'll see the wires are actually strapped to the wall. They're strapped in place. So when they turn the currents on, these large forces of repulsion aren't enough to rip the wires off the wall. They're held in place because otherwise they would rip each other apart and they would actually cause some very dangerous situations.